live. Hi everyone, this is Ron Batum with Atlanta Functional Programming. Welcome to another episode of the Common Lisp Study Group. Today we'll be continuing our exploration of the Lisp Interface Library that we've been covering the last couple of weeks. Last time we started down the path of defining our own interface, specifically one that handles some generic operations on top of sequence data structures, in an effort to actually go in and especially leverage some of the built-in functionalities for actual sequences, because we discovered last time when we actually were covering this that the sequence interface as provided by the actual library itself was not completely implemented, and it was a pretty decent use case to actually cover. Specifically, we went ahead and implemented one of the four interfaces that we thought would, two of the four interfaces that we thought would constitute what a sequence interface would, kind of require most generic algorithms to leverage in order for the generic algorithms to be implemented correctly. Specifically, we implemented the sizable interface as well as the emptyable interface. So I went ahead and defined, I went ahead and defined and wrote some documentation and posted this interface on Atlanta FP's GitHub repository as part of our Lisp Interface tutorial. Those of you who are interested in actually downloading this and playing around with this particular interface or getting some notes on it, the documentation isn't complete yet. I'm still working on that. I'm hoping to get through that today a little bit, as well as providing some more documentation on the actual interfaces as we go through. So today we're going to actually implement both the foldable and copyable interface. Last time we discovered when we were looking at foldable especially that foldable actually implemented a couple of concepts that we did not actually cover as of yet. Specifically, the Monoid interface that's provided by the Lisp Interface Library, as well as a couple of other functions that might end up leading us towards monadic transformers that's actually also available. I hope, to be quite honest, that we don't actually get to monadic transformers just yet, because honestly, to understand monads, it's going to be a lecture of itself, as well as handling even applicatives for that matter. So today we're going to be covering mainly monoids, and even I'm hopefully going to also cover the modeling effects, especially ones that are dealing with moving between pure and stateful data structures in the library, because one of the advantages of using the Lisp Interface Library is that you could write purely persistent data structures, and when you need to actually move over to probably a stateful version of that data structure, you can certainly do so by writing a small transformation chain, documenting that it's becoming a mutating transformation, doing whatever additional stuff that you'd want to do with that mutating transformation, and then bring it back to a pure transformation. Now, there are some consequences of doing that, but you can actually move from pure to stateful and stateful to pure and vice versa. And depending upon your use case, one might be better than the other, and you might end up getting some good performance benefits by moving into one versus the other. So that's what we're going to be covering today. I'm just going to... Hello. So let's go ahead and get started here. Let me just do one thing to keep an eye out for. That is...
Is this your library, Rob?
What?
Is this your library?
This is not my library. This is Fari's library, actually.
Oh, Fari. Okay. Yeah, he doesn't really use Common Lisp anymore. I never really heard of this one, though. So I thought it was perfect.
Yeah, so this is Fari. I've been trying to see if there's a way for me to pick his brain, because this is actually a pretty decent library. It just wasn't as fully documented as I thought it would be. But there was a paper that I've been kind of extracting information out of that I've been kind of covering, as well as figuring out stuff on my own. So
the best way to get a hold of Fari is if you go on Gitter. He's in the gerbil scheme channel.
yeah, he's been writing a lot of gerbil scheme. I
Yeah.
I actually saw his talk on.
I've ever been able to get a hold of him. He's really not on IRC or anything anymore. So if you have any questions, you can find him there. What is this? What is like? Can you give like a one-sentence overview of what this library does without diving in too deep? Because I missed the last couple weeks.
Yeah, sure. Just to recap for you and those of you who are on the stream, the Lisp Interface Library, again, is a library of data structures and algorithms that encompass a design style called interface passing style. The idea of it being that you can write generic algorithms much like you could in C++, ML, and so forth, and get the same parametric polymorphic benefits that those language provides in those features with this Lisp interface library and this interface passing style design pattern. And
is that anything like message passing?
It isn't so much message passing, more than.
I know that's what he's really into that. Hence, gerbil scheme.
Yeah, he had some trouble. My understanding is he's been trying to get into more in the concurrency and message passing semantics, and there were some limitations that he hit, or either community-wise, ecosystem-wise, or what have you, that kind of forced him into a situation where he had to move over to Scheme. I don't know all the details behind it. I can say that in terms of this particular library, some of it is fully implemented, but it's not. Some parts are not as developed as others, and that's because I think it's just mainly demand. Folks didn't recognize this library and its importance in terms of the design metrics that it was promoting. And there were other ideas that were bouncing around at the time that he published this, and as a result, he kind of I think gave up on continuing this development unless explicitly asked to do more work on it. I'm just trying to document what's available and figure out what I think is pretty useful, and see if there's any way that I can work on his work in such a way that we can at least build on it and make it a little bit more full-featured. There's not to say that there isn't a lot of features in it. I mean, there's a lot of data structures already built on it, a lot of interfaces built around it. It's just some parts related to sequences that we're covering today are not complete, and which is not a big deal because it's actually a pretty simple interface that we're gonna go through and we're trying to finish up.
Okay.
So let's talk about the sequence interface just to briefly cover it one more time as to what we're trying to accomplish here. This interface represents kind of generic operations that are going to be common to all sequence-style objects. We defined last time that the sequence interface objects kind of have to have the following qualities. Any object that adheres to this interface should have these qualities. It should have a size. It should be able to be reduced, meaning it is a foldable object. It should be copyable, and it can be an empty. You can have empty sequences of any sort. So what we discovered last time was that the Lisp Interface Library actually has already interfaces defined for these. And remember, these are abstract interfaces, meaning that you can't actually instantiate them. And what we're doing here by defining the sequence interfaces is we're creating a concrete realization of these other interfaces. Okay. Remember, in the Lisp Interface Library, interfaces are passed around as first-class objects. This is one of the ways that we take advantage of ad hoc polymorphism, particularly the ad hoc polymorphism provided by the Common Lisp Object System, and using that dispatching mechanism and dispatching on the interface to give us, a form of parametric polymorphism. We're actually building, this library builds parametric polymorphism on top of ad hoc polymorphism. Okay. We also defined, some of these functions. These, again, to reiterate some of the stuff that we did last time. When you define an interface or implement a concrete interface that inherits from other super interfaces, a lot of these interfaces have generic functions that are defined like this. This is just a macro that expands to something called defined interface generic. Oh, 1 second. And defined interface generic basically injects the interface or additional interfaces into its def generic definition when it gets actually created and registered into the system. When you want to go and implement those things, obviously you have to then write just simply def methods. You could go ahead and write it this way. Another way of actually implementing this is using something called define interface method. I'm using the def method approach just because for me it's a little bit cleaner, number one, but more importantly, if you read a lot of the examples in the library, although define interface method is available, a lot of places in the library uses the def method with this specialization. So I'm just adopting kind of a pattern for consistency's sake. Additionally, for folks who are unfamiliar with some of the stuff with the Mtable interface specifically, when we were dealing with predicates last time, recall that we had to make some specializations specifically on empty objects that adhere to the sequence interface, so that way we can actually use the empty predicate function on top of empty lists and empty sequences. So this is why this specific method has two specializations, one if it's empty and one if it's actually an instance of a sequence. So in the first case, if you pass in nil, essentially the null object, it'll take into the first predicate. Otherwise, if you give it an actual instance of a sequence object, it will go here and check to make sure that the actual instance is empty or not. So let's talk about Foldable. We're going to first start with a couple of the more obvious functions. I'm going to later defer our monoid discussion to later on in the presentation, in the conversation. So this way we can actually cover some of these a little bit better, and we can actually implement some of these codes pretty quickly. So again, unlike Haskell and stuff, other languages where we're implementing foldable objects and we provide types on this, we're actually just doing, again, like before, we're implementing the actual function has a specialization on a particular object using a def method, okay? Because again, these are all class objects that we're creating. So in the case of this first function, these couple of fold functions, we're just going to go ahead and do the same thing. So let me just go ahead and implement the declarations here so we can get going. So the first thing we need to do is, I think I just need to do fold left for the time being. Obviously, we could see that the first argument is going to be our foldable interface. In this case, our foldable interface is going to be a sequence object. The foldable, if I recall, is going to be the actual list that we're going to be dealing with. The function is going to be the function that we're applying to the list when we're doing the folding, the reduction, that is. And the seed is the initial value. So as you could clearly see in the documentation, this is what it's defined. Now, for folks who haven't actually seen this and are wondering what the difference is between fold left and fold right, So coming in from other languages that don't have a fold left and fold right, it might be a little surprising because you're like, well, reduce is reduce, right? But there is an actual ordering. Typically, when you are using reductions in, say, a language like, say, Python that actually has a reduce function, it's doing actually, for all intents and purposes, a fold left. It is taking the initial value, starting with the first element of the collection, and keeps on reducing until it has no more elements in the collection to reduce from. But you could also do a fold right, which technically is nothing more than a fold left on the reverse list. But and it could be implemented that way. But you can also implement it in other ways, where you start from the end of the list and go backwards using a reverse iteration.
Both ways.
What?
Common Lisp has both ways.
It does. I think it's from end, right? If you do reduce, I don't remember.
Yes. Yep.
Yeah. So in the case of sequences, we do have this ability to use just reduce, and like Michael just said, reduce has an argument that allows us to tell us whether or not we're doing fold left or fold right, and that makes us.
Most of the functions in CL that iterate over sequences take the same API basically from and key test, like all those. Well, there's no test in this one, obviously, it doesn't make sense. But they all have the same keywords. So if you always want to work from the end, just look for the front end keyword. Like that's very useful for like remove duplicates or something like that.
So to review this, actually, I may as well just go through the reduce signature here. We can see that reduce actually has quite a few different keyword arguments because it allows you to also reduce slices. You could do subsections, subsequences inside of reduce, as well as starting from forwards or backwards. You could, in this case, since we're doing fold left, we are just using the defaults. We don't actually need to change the defaults of anything passed into reduce. We just need to pass in the initial value. The initial value is obviously going to be a seed. And just to making sure that we are actually implementing what is defined, we're going to just double check here. Fold the foldable accumulating from the seed, iterating from notional left to notional right. Function takes as parameters accumulated value as a single value for the current content of each newly accumulated value. Okay, so we.
I have a question.
Yeah, sure. What's up?
Like the API for this fold left of lil here, it just takes a foldable, a function, and a seed.
That's right.
But like, what if the sequence that you want to fold, like you only want to, like say the sequence is a list of lists, and you want to pass in a key to reduce to only work with the cards. How would you do that?
You would have to first, I think, flatten, or you'd have to create what's called a monadic transformer to convert it into a form that would then become foldable the way you want it to. At least that's my understanding on how this library works. So there's
at first glance, it doesn't seem as extensible as the Common Lisp API.
Well, the Common Lisp API, this is one of the goals of the Lisp Interface Library was to create a consistent API across as many data structures that adhere to a specific, type or type hierarchy, because then you could write generic functions against that type family, right? These signatures, my understanding, at least for foldable, and again, I can't really justify or really think what Fari's doing, like what his thinking was when he implemented this way. But my understanding, at least from the papers, the presentation, his 2012 presentation on this library, as well as reading some of the interfaces that are available in this, is that a lot of the interfaces that he defined are using the same kind of signatures one would see if one came from languages such as Haskell or OCaml, that has a lot of these kind of built into their interfaces. That's kind of what I understood. Now, whether or not that's
most of those languages don't have like things like the key and the test function and stuff like that.
right,
And they encode that information inside the higher order function that's passed in.
right, right.
So I guess you would have to wrap that logic in your function that you passed in instead of like a keyword argument.
Right, and I think that intuition is correct. You have to encode whatever additional information you need to do in terms of checks inside the function that's being passed through into these higher order functions. So let's go and quickly implement these other three. So fold left star, I just got to make sure what the difference is, because I've seen fold left and fold right are pretty easy to implement, because again, we could just simply take our fold left, replace this with fold right, and the only difference between fold left and fold right is, one second, what did I do? Okay. Okay, let's go ahead and do that. And the only difference between fold left and fold right is, again, instead of initial value, along with initial value, see, we'd have to actually pass in the keyword argument that from end is true. From end.
If anybody's familiar with other languages that have fold right, could you please enlighten me on when it's useful over fold left? Because I've never needed to use from end.
All right, so
hey Rom.
Yes.
Yeah, I can jump in here real quick. The reason that you might want to not use fold right is if you have an infinite data structure.
Okay, yeah, that makes sense. So
yeah, it's very easy win right there.
There you go. All right, thank you.
Mm-hmm.
Right. So you want to use, if you have an infinite data structure, forget about fold right.
So when would you want to use fold right? Because fold left is the default in Common Lisp, and I never needed to use fold right at all.
So fold right would be useful. I could tell you one way. One simple situation is if you're trying to do composition, function composition, and you're trying to apply it correctly from right to left. Because remember, when you're doing function composition, the rightmost argument is the first argument that you are applying first, right? And its output goes in to every argument to its left. So you could simply use reduce to actually, a fold right to actually go ahead and do function application on a composed function. That way, a list of functions.
Okay.
Does that make sense?
Okay, thank you.
Yeah, no problem. Because that is effectively a fold right, by the way. I mean, if you think about it, right? You're at the rightmost function, you're applying it to the first argument, and you're passing it to the left. So it's, there are probably other cases where it becomes useful. That's just the most immediate one that comes to mind. So what is the difference between these stars here? Let me just read this guy. Fold the foldable with the function accumulating, blah, blah, blah. As many. The function takes as parameters an accumulated value followed by as many values as makes sense for that specific interface. Elements of a set, element and count for. The signature doesn't really actually tell me that I can pass in a multiset in here, but it looks like as long as the multiset is foldable and you implement it for a multiset correctly, this should work. Okay. I'm going to implement this the same way that I would have implemented fold left, but I don't know if this is correct in terms of the definition here. So folks who says that's not how you should implement it, let me know. But this is kind of where I am coming from based on my understanding of this.
Are there any example implementations of this protocol already in the library?
I think there might be one for this guy. Let me go and look at it. 1 second. Let me just
that
first.
Is a little confusing to read.
Let me just go clear that up. Okay, so specializes on fold left. No references? Come on, there has to be a reference. You know what? I bet you it's because there's a pure version of this guy. 1 second. Let's see, apropos. Let's do apropos on fold left star. Let's see here. These are all interfaces. These are all interfaces. Here we go. Dang it. Why can't I jump to the definition?
It's a generic function. It's not a method.
Yeah, it's not a method. Yeah. Okay. These are all generic functions, but I don't see any implementations. But you know what? I bet you.
You can use the Doom search.
Doom search. I don't know what Doom search is.
You're using Doom, right?
Yeah, I am using Doom.
I think it's like space S. And then search entire project isn't that like capital lowercase p?
Search project is my project. I think they do use search other project. No, these are all available projects. That's not what I needed. Let me do this.
Space PA will add a new project to your Doom project.
Give me just 1 second. What I'm going to do is I'm going to do who specializes Posh left. Dang it. Okay, there's nothing who specializes that. Let's see if Classy actually implements it. 1 second. Let's go to... No, not local projects. What am I doing? It is Lisp. It's quick Lisp. It's quick Lisp. This is how I have to go into the actual code. So I'm just I think it's software or installed software. I think is where it is. Yeah, there we go. Lisp Interface Library. This guy. Interface. No, not interface. Transform. Classy.lisp. Yeah, classy.lisp. Okay. Let's see this guy. Let me increase the size because I just realized from looking at earlier that I forgot to increase. My apologies for folks watching. I will re-show that code later on, so you guys can get used to it. Let's see, fold left. It says it implemented it, but I don't see anybody who's actually implemented it. These are all interfaces that he's already defined, right? Yeah, this is just implementing the standard. Okay. That's not it. Let's see. You know what? This is where grep becomes very useful. Let me open up eShell. And I'll go into that directory and just...
Can you hear me?
Yes, can you hear me?
I can hear.
Okay, cool. Because if neither you can hear me, that means then there's a problem with the stream. Guaranteed problem with the stream. Let's see here. Fold left on this guy. Let's see now. Tree Lisp. Ah, here we go. Tree implementation. Hash table implementation. So a lot of his implementations of these and realizations of these functions are based on essentially the map. Like he actually spent a lot of time implementing the associative list interfaces and getting concrete versions of those. I think it's based on his needs to make sure that it works the way he expected to. Let's see here. Fold left I binary tree. If empty, if the node is empty, that makes sense. Otherwise, we'll keep fold lefting on the accumulated value, which is fun called on the actual argument. And the seed. Okay, so he implemented this based on the lower level fold left for a actual node. Is the node defined here?
Node class.
Doesn't look like it. So it's going to have to be in this guy. Where is the node classes? Looks like no, that's not it. Let me see if hash table gives me a better collection on this. Hey, where are you? Fold hash table. Oh wait, let me look at this. This might be. Huh. Okay. Yeah, I am doing it right. It looks like his implementation still used a various reduction. In this case, like you can see right here, for example, fold left star and fold right star. I don't think he defined fold left and fold right for this specific. Yeah, he did not. He did not define fold left and fold right. He just defined fold left star and fold right star, which means in some cases, if you're implementing, that makes sense because for stateful objects, it's easier to write a fold left star than it is for a fold left. I think based on his definition of what a fold left is and a fold right is. Okay, so we can just implement fold left star and fold right star the same way for sequences. Great, that's fantastic. I don't need to do much work. All right, let me go ahead and do that. Close this guy out. Bring up our sequence. And let's go ahead. And since one of the nice things is since we've already implemented fold left, I could just simply do fold left I. Our foldable, which is obviously going to be the same thing as before, our function and our seed. And we could do the same thing here with fold right. Fold left, fold right. Done. Okay. So we've now implemented about 2/3 of our foldable interface, all right? But what about the remaining ones? In order for us to actually talk about these other two fold methods and actually get into how might we implement them, I have to first discuss a concept about called monoids, which we haven't covered on this stream, and it's not a fairly complicated concept, but it is a concept that I hope Judd, you will step in and correct me if I'm wrong. All right?
What's it?
From what I hear, it's a very uncomplicated concept, but it's very complicated to explain. Someone's done it right.
Okay.
Right.
Again, what are we dealing with here?
Monoids.
Oh, it's so dead simple.
I know it's dead simple, but if I say it wrong, you could say, you said it wrong, all right? So
Okay. Here to help.
All right, that's all I'm saying, all right? A monoid at its heart is nothing more than a set, all right? A set of elements, all right, with an associative binary operation, that is a function that you can apply associatively, and an identity element. That's an element that is kind of, you could say, the most indivisible portion. It's the identity of that set. You can, an identity element is usually something where you apply any function to this identity and another element that's in that set, and you get the element that you passed into the operation, not the identity. An example of this is like the 0 element in numbers, and if we're using the associative binary operation for addition.
Specifically, okay. All right. Let me jump in. This goes back, Ron, to your and my discussion. I think that people get hung up kind of because they say algebraic data types rather than saying data type algebras, right? So all an algebra is a set of symbols, a set of operators, and a set of transformation rules. That's all. So this, the magic value for any algebra is the value that doesn't change the other thing in the binary operation.
Right.
So in the case of, if you say numbers, we're getting a little ahead of ourselves, right? Because we can certainly define an algebra specifically for addition, right? And in which case the identity is 0.
Right.
Right? Anything plus 0 is itself, obviously, left or right. Same thing if we switch to a different algebra, and this is actually kind of slick, right? So kids grow up knowing multiple algebras. Right? They know the addition algebra, then Jesus Christ, here's the multiplication algebra, in which case the special operator is 1. Right? Anything times 1 is itself, and left or right doesn't matter. So, grabbing that intuition and saying there may be other cases where a log plus some boring event equals nothing, right? Equals whatever I had before. Or anything, right? Any data structure, and this is the thing. Again, with was it Beckwith, Brian Beckwith? He's like, look,
Brian Beckman. So for folks, for reference here, for folks who are on the stream who aren't familiar, Brian Beckman is a Microsoft researcher who gave a very excellent talk about this. I'll put the URL to his explanation. It's titled "Don't Fear the Monad," where he goes from monoids to monads, and he teaches it in a very simplistic fashion. But we're getting ahead of ourselves. I think just simply with the definition is very simple. You have a binary operation, all right, just a function for some set, all right, and an identity element. What's an identity element? The identity element, it has Judd already explained, is an element that's in that set, such that if you apply the binary operation with the identity element and any other element, you get the original element back. And the example that's most canonical when we talk about the identity elements, especially when we're first introducing it, is 0 under the operation of addition. Because any element plus 0 is always going to be itself. So any element x plus 0 is going to be x. All right? And it doesn't matter if you do commutativity, but we're not going to talk about 0 plus x or x plus 0. Since the only requirement is associativity, right? That's a very important thing to recognize, right? When we're talking about monoids, and especially some of this kind of algebra stuff, the definition becomes important. So to remind ourselves, I'm going to give you a very quick lesson of some of these operations and these definitions. When we're talking about commutativity, right, we're talking about essentially a plus b equals b plus a. All right, you could switch the arguments on the operation. It doesn't really matter. You'll get the same result. When we're talking about associativity, okay, and this is very specific for monoids, it's really related to how do you apply the reduction, right? So in this case, where do you put the parentheses first and do the operations first? And you can see that in this case, regardless of where you put the parentheses, because of the order of operations, you'll end up getting the same result regardless, right? That's just, it's related to specifically partitioning and figuring out function application. But it's important when we're talking about monoids, because that's a very important requirement in order for something to be a monoid. It has to be an associative binary operation, and it has to have an identity element. All right. So how does this relate to monoid fold and monoid fold star? All right. So let's look at what this monoid fold is. It says fold the foldable according to the monoid interface, where each entry is mapped to the monoid using the provided function. So what is the monoid interface? Because we have to go and see how, what functions we have to define in order for us to make our sequence monoidal, if you will. All right. So we have to go and look into this interface. So let's go ahead and look into that. I think it is in interface, not monad. I hope it's not in monad, because that would be very upsetting. Monoid. Nope. But all right. So I have to do an apropos on this guy. MHA monoid. Where are you? Group.lisp. All right. Okay. Let's get to what? Oh, sorry. For some reason, it decided to.
Wonder what magma is.
Oh yeah, there's a lot of stuff in this in this library related to like different mathematical concepts. I don't remember what magma was, but it's related to some math concept for dealing with sets. So, and no, it's not about volcanoes. That I could say for sure. Sequence.lisp. All right. This is going to be a semigroup. Well, what's a semigroup? What's a semigroup? A semigroup is a magma. And what's a magma? A magma has...
You gotta know it all anyway.
Yeah, it has to go all the way through. So, let's see. Oh, okay. A magma is defining is any type that has an operation that can take in two values and return a value. So this is just defining an operation. So you need to define an operation. If you can define an operation, if you then define a semigroup that has an op list function, and that function takes in a list, and returns, if not a monoid, the list must be non-empty. But if it is a monoid, it could be empty. Right. That's because you can handle the empty list in that case. All right. So this is like I said, monoid itself is a fairly simple concept, but how it's implemented is he's breaking it down in the Lisp Interface Library to its very low level indivisible terms. So like a monoid is an associative, like I said, it has an associative operation and an identity element. This semigroup, okay, is defining the associative operation. Okay, it's implementing, by defining this op/list on a list, you are defining essentially the associativity, okay, for a given op, for a given operator that you're trying to close this monoid under, okay. Identity, the identity interface, which is also of type magma, is because in order for you to operate on an identity element, you need to be able to close that identity element under that operator. So it's separating the identity element of a set from the actual operation on elements of that set. Now, I know for the pure Haskellers in the audience, all right, and the MLers, that I am fudging terms here and kind of polluting them to restrict it within sets, okay? For all intents and purposes, at least with respect to types inside any programming language, dealing with sets is not necessarily a bad thing, okay? But if you really want to technically be, if we really want to be very accurate in terms of our descriptions and definitions, technically speaking, a monoid essentially is dealing with objects inside of a category, and but I really don't want to introduce category theory into this discussion.
Category theory is a whole nother can of worms.
Right. So I'm not going to go there. I'm only merely mentioning it just so that for folks who are interested and for the pure Haskeller audiences, I know the people who what the difference is. I'm just restricting it for simplicity's sake. All right. My apologies. Let's move on. I don't think I need to actually implement these guys. I just think I just need to implement an operator for the magma, but it might be okay. I don't think I need to do anything much. Let me just go and double check for other folks that implement this guy. What?
George.
Was there a comment?
Yeah, it was the I can never remember which one. SICP.
Was it Sussman or was it a Belson?
I can't remember. That's why I can't remember. Anyway, he goes like, "Don't pester me with category theory." You're really pissed off. It's like the funniest thing I've seen from MIT ever.
You got to find the video because I'd like to post it. You know, I'd like to.
For today. Yeah.
Okay, so let me just go ahead and look at some of the examples that are already available for folks who implemented monoid fold. Let's see, who implemented monoid fold? Okay, swear. Okay, I'm using apropos instead of specializations. Give me a second. I need to go back here, go into this directory, quit that, go down down here, split my window so I can actually have. Okay, hold on. This, there. What? That's funny. Doom Emacs will not allow me to split the window where the REPL is. That's hilarious. Okay.
Yeah, that's not a window. It's a pop-up.
That's a pop-up? Oh, okay. Good to know.
It's not a real window.
Where is my buffer? Give me e shell. That's one. Okay. Let's go here and call this monoid what is it? Monoid fold is what it's called. Okay. Let's see who implemented monoid fold. The hash table has an implementation.
I see you using grep a lot. You could just use space sp.
Space sp.
It's all interactive. Yeah, same thing.
Yeah, I'm sorry. I'm so used to
I mean, it just prevents you from opening a shell and all these windows. It's a lot simpler if you can get in the habit of it. Saves some time.
Couldn't find rip grep in your path.
Oh, well then yeah, you have to install that for doing the work correctly.
Good to know.
Well, forget it for now then.
Good to know. Start eShell. Okay. Let's go back to this. So we have monoid fold in the hash table implementation, but I don't think let me just bring that in. This is going into the hash table implementation. Let's do the app implementation with interface, if empty. Okay, he actually implemented this as a cond. So for folks looking at this and says, Rom, you're talking about monoid fold, but you're using map monoid fold from divide or map monoid fold star from divide / list and all this. Just to quickly mention these and saying that these are kind of completely irrelevant to the discussion is I have to at least bring it up so folks are aware. For a lot of the interfaces, the Lisp Interface Library provides mixins with predefined implementations of common functions so that you don't have to necessarily implement those semantics in your own interfaces if you just simply inherit from those mixins, which allows you to then, as a result, leverage already predefined generic algorithms and functions that have already been specialized for those specific mixins. This kind of actually enables a separation of concerns almost. So this way, especially if you're just writing, a very specific or specialized variant of an existing data structure, and you just want the same semantics with some additional functionality. You could certainly do so by just adding that for your specific type, but inherit from these mixins. And then thanks to method combination in class, it'll go ahead and unify all those into something that will then get applied accordingly. It's pretty awesome because then the way you would implement any common data structure really becomes, well, what mixins are already available for the generic types? How do I just go and update it for my own specific thing? Let's see here. I think I saw something for a fold on set. This is set for multi-set. No, that's not it. Yeah. Oftentimes when I've been going through this this adventure, honestly, because of some of the documentation missing, I was like, well, I have to go and look at the examples in the code to figure out what the best way to actually do this. So for folks who are like, oh, this looks like a really good library, but I'm going to have to spend a lot of time reading through it. it's kind of the lesson I've learned too. There's just so many things in here, but some of it isn't documented in such a way that folks can actually go and easily navigate through it. You have to go and look at the code to actually get what you want. But he did a great job at least documenting the interfaces. Say that again?
Something specific to this library, Lisp in general, pretty much.
Yeah, well, I'm just bearing some mention to this one because some libraries, although there isn't much documentation, the interfaces and the use case is somewhat simple enough that you can intuitively figure out how things kind of work. But in this particular case, I've been kind of struggling just because there's just so many things available, so I have to go and see how he implemented a specific thing. Interesting. Here we go. So what he did is map fold right from fold. Oh wait, this is the wrong thing. I'm looking at map instead of monoid fold. Monoid fold. Here we go. Monoid. He implemented specializations for map. And I want a sequence to actually handle this. The only way to know this is going to take a little bit more than I anticipated when I was looking through this. Let's see here. Generic star interfaces goes into what? Let me look at the hash table one more time just to see what he did. He did monoid fold, the hash map interface, which itself is a thing. Map. Got it. I see why this was confusing me. Alright, so in order for us to do this, we're going to have to do essentially what he did here. Let's go ahead and do that to make things a little easier for ourselves for sequences. Okay, so let me explain my design here. This is going to be a little bit of a... Okay. So the first thing that we need to do is... Oh, shoot. I got to go bring back Mr. Foldable. The Foldable fold.lisp. Okay. So... So the first thing we need to do is we're going to go ahead and interface. We're going to go and define this using fold, monoid fold. Okay. And you'll notice that the monoid fold is taking in 4 arguments. The first one is going to be obviously our first one. It's going to be our sequence object. The second argument is going to be, of course, the monoid interface. Now, the monoid interface that you're dealing with is going to be a specialized version of this folding object that we're going to have. But the difference is it's going to do some checks on the operations that you're providing. So, like in the case of this function here, okay, the last argument, the function. The monoid interface, what it's going to do is it's going to actually take that function and verify that it's it adheres to being a semigroup specifically and has an identity element and so forth. Now, in the case of sequences, okay, specifically Lisp sequences, because those are fairly well defined, I don't necessarily have to actually use the monoid interface. Now, To actually implement that, though, I could go ahead and add some extra overrides to essentially, verify that the function that I'm using is appropriately associative. The types that are available in the foldable object are accordingly have an identity element and so forth. But this is where the type checking piece of Lisp, the Lisp Interface Library comes in. And I really think that that deserves an entire talk on its own, because check invariant itself has some complexity that I have to actually go and understand in order for me to really show you where it's appropriate. Like I mentioned before, the check invariant function that's available in the Lisp Interface Library will take an interface object and an instance and make sure that it validates that object adheres to that interface, but it's a very expensive operation. And the examples that we've seen so far in the source code does not use that explicitly. This is why in some cases, especially in the monoid fold case, it's difficult to recognize whether or not a function is actually behind the scenes using just a type dispatch to dispatch to another version of the function that implements the monoid interface, or whether or not it actually goes in and does something more towards the fact of validating the input arguments before it actually implements the algorithm. A lot of that stuff was taken out when Lisp goes in. The Lisp Interface Library went into kind of a production mode because of the fact that it is an expensive runtime cost to actually do all that type checking, especially when the function gets invoked. Now, it requires a little bit more experimentation. But if you bear with me, I'm just going to go ahead and implement this the way we currently have it, ignoring the monoid operation for now. Just merely because, again, like I said, we're dealing with Lisp sequences here. It is not necessary to really think about the associativity of the operations for now. Of course, obviously, when you're dealing with sequences in general, we'd want to make this more correct. So we'll go through a second pass and actually go and implement some of the more type checks later on, if we have time today, but definitely once I get more details on how to actually implement that correctly. I hope that makes sense for folks. There is a comment about larger font. Okay, give me 1 second. I will increase the font size here, especially here. I think I have to go with that one. Let me pull. Let me save this guy. And let me go ahead and implement this for the time being as fold. I'm defaulting to fold left just because that kind of keeps us in the same realm as. Problem is I can't just simply do fold left because the foldable function there doesn't take in a seed, which is hilarious. Is mapped to the monoid using the provided function. Let's see here. How do we do this? How do we make this into a monoid? Let me go back to what that was doing. Okay, so let's go and look at what this is doing in terms of took monoid hash. Foldable and the Lambda bucket. Okay, so this will be essentially, let's see here. the monoid fold star. We need to implement it this same way, I'm thinking. We have to do now, what is the foldable object that we're dealing with? Well, we're dealing with sequences, so we're going to go ahead and pass that in. We need to also implement let's see here. It's going to take in the monoid interface, but the monoid interface was not implemented yet. Let me see who implements the monoid interface. Who specializes on Mr. Monoid? References. Sorry, I have to actually technically put this as a group. Monoid. Just monoid. No one. Interesting. Again, let me go and pull up eShell. Let's see who deals with monoid. Let's see. Semi-group identity. Monoid fold map function. This guy takes in see, this one takes in, pull that up. This guy is going to take in 973. Oh, okay. Okay. So I can use fold left, but I have to actually specify ID on the monoid. Okay. Let me see if I could do that already for any given thing. Let's see here. ID given the identity on the monoid. Right, that makes sense. That actually makes sense. Give me a second here. Now I'm starting to see the light on how to implement this. Sequence. It took a while, right? It took a while, but I started seeing the light on how to implement this. Let's see here. This takes in the monoid. This can be implemented using a fold left. So I was right that we can actually use fold left. What does fold left require? Fold left requires that we use wait a second. Why is that giving me that? Interesting. What? Okay. I don't know why it's not giving me the function signature, but let me go and take out these. Take out that. Put in the fold.lisp. Okay. Let's bring this down to what we had earlier. Okay. So now, monoid fold can be implemented using fold left because, again, we can actually define for a given type. To make this a monoid, we have to give an identity element, right? So we could define the identity element specialization on that monoid, and then for any given type, we could say if you pass in this monoid, the sequence, and it is a monoid, then the element that it's going to be, the identity element is going to be whatever the type of the identity element is. So if the sequence is of integers, you could say the identity element is 0 and so forth. We'll go ahead and implement that. But the simplest way of implementing the actual fold left guy is we're going to pass in sequence. Hold on 1 second. Let's pull up our fold left here so that we actually put in the right. We pass in the foldable. We pass in the function. Okay. Now for the seed, instead of passing in the seed, what we're doing is we're doing ID. Okay. And actually, little interface, I think it's group ID on the identity. And the identity here is going to be essentially the monoid, because a monoid is an identity. Remember what we saw earlier, okay? Let me just do this. Okay, 1 second. Oops, sorry. Little interface, that's the reason why I wasn't getting it right. Okay. Just make sure. Fold left. So now this is done. So now how do we implement? Okay, so before I implement fold star, just in case there are folks that are watching and having questions, remember ID takes in an identity interface, okay? And remember what we saw earlier with the definition of a monoid, okay? And I'm going to bring up the definition of the monoid again. Ignoring the magma stuff, all right? I'm not going to get into that. The identity element essentially is nothing more than the identity of the interface that you passed in. And in this case, it's taking in the actual interface type only. It's not taking in anything else, okay? As you can see by the function signature there. Although, just a question, Michael, do you know how to increase the size of the mini buffer in terms of the font size? Out of curiosity, Emacs? There has to be a way.
If you press space,
I can't get into the mini buffer when I'm in there, so
press space. Get your Doom menu open.
Oh, okay, got it.
Space. Is there a toggle? I think it's under like T or something. Yeah, T.
T? Okay.
T for toggle.
Oh, toggle, got it.
And big mode, B.
Holy crap. Okay.
But now that you changed all your buffers individually, you're going to have to decrease them back to normal.
Yeah.
But that's a quick way to make everything big all at once.
Okay.
Including the mini buffer.
Oh.
So you don't have to mess around with individual font sizes.
Okay, I'm gonna first.
Now that you know that.
Now that I know this really helps me because that I don't have to do any kind of nonsense like this anymore.
Yeah, if anybody says the font's too small, you just hit 2 buttons and you're done.
Yes. I did not realize that. Thank you. That was a little... Okay, cool. Fantastic. Excellent. Okay, this actually works.
Your rep was still kind of big, but that's okay.
There's not much I could do, man. Not much I could do. Sorry, I just screwed up that. Okay. Jeez. Okay. Oh, shoot. Okay. Folks watching, yes, I had to do just some Emacs adjustments here, just for folks getting a decent large font. So this way, we don't have to worry about this anymore. And to make things a little easier for ourselves, I'm just going to go ahead and, if you guys don't mind, I'm just going to change some of the indentation here just so that we could get everything fit on one single screen instead of scrolling ourselves around. All right, so this identity element is already defined for us, okay, as part of the Monoid interface, okay. I'm not going to demo this particular function just yet. I'm going to use that later on for other discussions, but I'm going to finally implement, the little interface fold monoid fold star too as well. May as well get that done and out of the way. And I'm going to implement this guy using the same thing that we did before. So if we're using fold left in monoid fold, we're going to be using fold left star, obviously, and monoid fold star. All right, just to make things a little bit more consistent. Here, as usual, I am putting in the full package definition. Folks who don't want to do this, certainly you can certainly use you could certainly use package. I generally advise against using use package. I don't know about other folks in the chat, but you know, it's just generally speaking, something that I try to avoid, just merely because I got burned enough times by that I just like, you know what, I'm not going to do this anymore.
It's extremely frowned upon.
Yeah.
That's what package local nickname itself.
So let's see here. Now we do fold left. We got our foldable, Mr. Foldable. We got our function, Mr. Function. And then again, just like before, we just need this. And we now have our fold left star. So we've now implemented existing, a couple of things should become very noticeable here. One, once you've defined kind of the lower level operations, just like we had before, okay, like in the case of fold left, fold right, you can start using them directly in your other specializations too as well. And as long as the function, the object that's passed in adheres to this top level interface, it can be safely assumed that these functions will exist and everything will, kind of work out in terms of actual code getting dispatched the way you expect it to. All right. So we have implemented the foldable interface. We have one more interface to actually implement, and that is copyable. So what does copyable look like, right? Oops, not delete. Let me split. Copyable, I don't remember where it is, so as usual, let's do our normal apropos, figure out the actual copyable interface to figure out where it is. Although for some reason it's taking its sweet time. Okay, so it's in the base class, which means I think it's in base.lisp. Pull this up here and do base copyable. Okay. So let me go ahead and comment this. Again, once we're done here, I will go ahead and check all this in so that you guys can look at it. And I'll also write up, put up a write-up to a markdown write-up of everything that we've done today, just so that we can keep track of what we'll be doing next time. I'm apologizing for we're covering a lot of the basic stuff here, but we haven't hit the pure versus stateful transformation stuff that I'd like to get through today. So let's see how quickly I can get this, and then we can handle that too as well. This section implements the copyable interface for the sequence. Okay. Actually, I should say not specialized. Is what I should say. And okay. So copyable obviously has just one function. Copy. All right. Not rocket science there. So we're gonna actually, and again, when you see these defined interfaces with the generic, okay, macro here, well, it's really like a keyword inside of the defined interface macro uses what we're ultimately doing is just to macro expand this, just to show this again. It automatically injects the name of the interface into the def generic function signature. All right, so in this case, copy is the name of the function. Copyable is going to be the first argument, and then our actual object is going to be the specialization that you're passing in. All right. So here, it's not going to be that big of a deal. We just need to go ahead and implement little interface base. Let me see if I can actually use all, because hopefully I prefer to use the top level function. Okay, copyable is going to be here. We're specializing this on our sequence interface, which itself is copyable, and the object that we're passing in, which is going to be some sort of sequence. So I'm just going to call it seek for simplicity's sake. Actually, you know what? Let me do this. Object seek is specialized on sequence, so that way we handle that correctly. All right. So how do we copy in Common Lisp for sequence objects? Think it's just simply. There's no copy function in Common Lisp, right? Yeah, there isn't. There's I just don't want to do a loop into a construction. Is there any? No, there's no copy, right? Yeah, there's no copy. That's what I was talking. What should I do? What's the best way of implementing this? And then, okay. No, if I do a loop, the problem is with loop is always going to return a collection. What I really need to do is I need to make sure that the types match. So if we pass in a vector, we return a vector. Okay, got it. I'm just going to implement it using map. Result type is going to be type of sequence. Okay. Function is going to be just the identity. Oh, right. Sorry. I don't need to use that anymore. That. And our first sequence is going to be just seek. That should just do it. Let's try that. Okay. Little interface all copy sequence. Object is going to be, let's try a list. 1, 2, 3, 4, 5. We get 1, 2, 3, 4, 5 correctly. Let's switch this over to a vector using the vector reader macro, and we're good. Okay. So this is all done. So folks watching this, this is your basic implementation of an interface customized for sequence objects. Okay, I'll go ahead and post this in our GitHub repository. Has a final review. Again, it's nothing more. It's just like implementing honestly, it's just like implementing a def class. The advantages of doing it, of this concrete implementation of the interface, again, is oops. Yeah. Just noticed that the stream was running, but you guys aren't available, so my apologies. The Hangout was disconnected. Don't know why.
Yeah, it did that to me twice already.
Yeah, that's really weird.
Be, probably because everybody's live streaming these days.
Yeah, more than likely. Okay, so where was I? Yeah, so just to reiterate, what we did was we implemented a sequence the sequence interface, a concrete interface of the sequence. Concrete interface for abstract interfaces for sizable, foldable, copyable, and emptyable. Okay. And the importance of this concrete interface is so that you can write specializations on this subtype family that you if you want to call it that, right? And as long as you have those specializations, thanks to method combination, you can get some you'll get for free some functionality for your data structures, especially if you use mix-ins. At the same time, you are leveraging parts of the actual Lisp Interface Library for creating a uniform API, regardless of what data structures you're using. Okay. Here we noticed that a couple of things that we needed to definitely get some understanding around. One is that because of this ability now to have parametric polymorphism using ad hoc polymorphism being available, one of the things that we now get to do, especially in this realm, which is pretty useful, is we could start talking about some of the more higher level concepts that are available in the more statically typed languages such as Haskell and ML because of this kind of design. Okay. Now, there's one caveat there that I wanted to be very, very clear about, and that is a lot of times when you're talking about some of those higher level concepts, specifically that I'm talking about monoids, functors, applicatives, and monads, okay, you are defining those on a series of generic types. Common Lisp, because it's dynamically typed, you could, during your development, make sure that a lot of that type checking is done correctly using type satisfies, dep type, and then using declare. You can add some optional type annotations into your functions to actually go in and do further compile time type checking, but you can't use the Lisp Interface Library, this built-in check invariant, because all that's done at runtime, from my understanding. And as a result of that, it'll be very expensive if you load it into your image and you have check invariants in a lot of places. So one recommendation that the library has kind of encouraged, and what I've been encouraging throughout this discussion, has been to, again, use check invariant where appropriate, and then go ahead and when you're ready, as you saw earlier, get rid of check invariant just so that people can have a bit more and document that. So with that said, we're closing in on our lovely exploration of this library, and I know that a lot of this has been a fire hose of information, especially since we are talking about now functors and monads, and as well as we're talking about pure versus stateful and so forth. We went a little over than I had anticipated to, because of the debugging that we were doing earlier. But next time, I'm going to cover one final piece and one final feature that's available in this library, and that's creating APIs and being able to transform between the pure interface and the stateful interface, and vice versa. And how do you go and write and what he likes to call a mutating and linearized interface, and we'll define those concepts and define those functions, and we'll go through that final piece of the API and that final piece of the library. But are there any questions about what we covered today?
Yeah, for the copy interface.
Yeah, sure.
Now, And your example in the REPL there, that's sort of like the basic case where you just have a flat sequence. But what if you had a nested sequence, like list of lists, say? Now, are the inner lists still references to the original list, or is it an actual deep copy?
I'm pretty sure it's a deep copy if I remember how map works. I don't think they do shared structure in this case. But I could we could verify that maybe. Let's see, what would be the best way of doing that? So let's try something here. Let's define a variable. Simple seek variable, and I'm going to go ahead and use our vector. Okay, and I'm going to go ahead and copy this. Hide. Sorry, I have to hide something here. Okay. I'm going to copy this vector, and let's go ahead and define seek copy, and kill this guy, and we're going to go to seek. Okay, so now we have 2 copies of this, and now what we'll do is I'll just do setf aref seek copy 0 3. All right. So now seek copy, the first element should be 3, and seek itself is going to be 1.
Yeah, that wasn't exactly my question.
Are you looking at lists of lists too? So you're looking at
yeah, do the same thing with like pairs instead of just 1, 2, 3, 4. Just do like a pair of 1 and 2 and a pair of 3 and 4, something like that. And then mutate just like the 3 or something.
Okay. So let's go ahead and change this, and let's copy this guy too as well. Okay, so now we have this guy and seek. Okay, and let's see, how do I do this? It will be setf. I think I could do kidr car. So kidr, I think is what I need to do. Of seek copy, and change that to say 5. Alright, so what is seek copy now? Shoot! That is not what I wanted to do. But that's okay. That's a dotted pair now. Let's see what sequence is. It is a shared structure, isn't it? So we need to do a deep copy here. How do we do a deep copy? A deep copy of the structure. How do I do that? That will be... Shoot. The easiest way for me, just because I'm not as familiar with all the map variants beyond map car and map, would be to write a loop and then make a new instance of it. But that's not what we should be doing.
See, deep copying in Common Lisp is like basically not a thing because you have to worry about object identities, and it's very domain specific as to what deep copying actually means. There are a few functions that do it in specialized ways built into the standard, such as copy tree. Will copy all the conses recursively in a nested list, giving you an identical structure that shares no structure with the original.
But can that work on... Yeah, I mean, it should work on all flat lists, but I didn't think that it would work on...
It'll work on any tree.
Oh, there's a copy sequence.
Yeah, copy sequence is different.
What does copy sequence do? Is it a shallow copy?
Yeah.
It's basically what I just implemented. Which is equal but not EQ. Okay. That's a bit disappointing. Wait, which is equal but not EQ. That's actually what we want, right? Because EQ means they're sharing the same object identity.
Yeah, you're copying the sequence, not any internal structure of that sequence, just the outer sequence.
Okay, so it doesn't recursively copy anything.
No, that would be copy tree, and it's only defined for lists.
Yeah, that sucks. So this will not work for vectors.
And even copy tree will not do deep copy because it only deals with conses. Like it actually deals with the tree structure of nested lists. Like if you were to have, say, a class object somewhere inside that list, that's obviously not going to be copied.
So I would have to figure out how to properly construct
Deep copying is a hard problem in Common Lisp, just because of object identity.
Yeah.
So you basically have to write your own for the specific domain you're working in, because there really is no generic solution. Kent Pittman gave a great talk on this. I should find the link to the description.
Interesting. There's shallow copies. To copy array, you have to write a routine. So that would.
Okay, so here's a link you can put in the description if you want to read more about why Common Lisp doesn't have deep copying.
Ken Pittman. Always awesome. Okay, let's see. So copy object, copy list, copy a list. There are so many different specializations. I can't copy. Why can I have a generic or polymorphic equal function? Common Lisp should ask this question, but rarely do. Suppose most programs are worth giving them a tool of reasonable engineering quality to get their work done. Interesting. Okay, so folks who are just tuning in, we're just discussing about the difficulties of implementing a proper deep copy in Common Lisp. Just mainly because it doesn't look like it's a thing due to the fact that it expects a lot of objects to be in EQ. And a lot of the equal representations, such as copy sequence, which is what we kind of implemented earlier using map, only does a shallow copy. So let me see this here. I want to see this. Oh shoot! Wait. Where are you? There we go. That was what I wanted to do. And let's see here. That's instead of using. I'm going to use ELT. Okay. And then ELT on C copy at the second element. And let's grab the car of that second element to, let's say, 5. Okay. So now C copy is 5, 4. Let's say seek Interesting. I'm wondering how a lot of these functional libraries, these functional data structure libraries that claim that they can't do modifications to it then, they probably are just constructing a brand new object from the ground up.
Yes. Are you talking about other languages?
No, like fset, for example. Fset always it looks like it's always creating a new sequence from this. So if that is the case, instead of doing copy sequence, what I should be doing is I should make a brand new sequence and then copy everything into it. So the best thing to do
Right, and it gets real complex when you have aggregate types, like like structures or class instances where you have some arcane value that there's no clear way to copy it. Like maybe there's not even a copy constructor for that, and it was initialized when you make instance in a special way. Like it gets really complicated. Like there's no way to copy every object. It's up to the end user. Like the implementation, the language itself has no idea how to copy something.
Right. I think in terms of structures, it's slightly easier though, because you could use the meta object protocol to hack up a copy, right? Saying based on the slots. Like I found a Stack Overflow post where the dude wrote essentially a deep copy function that goes and uses essentially the mop to figure out the direct slots and then use those to actually go in and recursively call on the actual slot structure to go and update every slot value in the brand new copy that they just created using copy structure. So I don't know if that's necessarily what you'd want to do here, because what we're doing is just simply a sequence of sequences here, but it's another option. That's an important point. Let me go ahead and make a comment here saying that note this currently implements a shallow but not deep copy due to the difficulties of implementing deep copies in Common Lisp. Alright.
It's not really a difficulty, it's just that deep copying assumes domain-specific knowledge of user-created data. It's kind of hard to explain, but the implementation has no idea on how something was created, so it can't recreate that.
So let me phrase it this way: some design consideration one must take. There we go. One must take when decopying. Deep copying data. Whether user defined or built-in. I know. I remember distinctively.
Like say you had like a binary tree inside of a sequence, right? And you were copying that sequence. When you get to the binary tree, then the Lisp implementation would need to know how to traverse that tree in order to reconstruct it. Like that's something the implementation can't figure out unless you as a developer give it that information.
Right, unless you actually tell it.
Yeah.
Yeah, I understand. I understand what you're saying. I'm just merely saying that that just tells me though that there is some additional stuff that I'm guessing this library, and I'm just talking within the context of the Lisp Interface Library right now. In order for this interface method to be correctly defined, there has to be some additional functions that this interface should provide in order for us to correctly implement a copy function. Saying, okay, are we doing deep or not? Okay, you need to override this method. Okay, it depends on what your data structure is on how you're going to copy this information. So to abstract it out, we're going to have to provide an interface method that says, okay, you're copying an object. Okay, what does that mean? In the case of what's passed into the collection type, and so forth. So I can do that generically. I just
And the other thing that Ken Pittman says is like, people usually just want like a generic copy that copies everything, right? But
right.
Like there's a difference between conses, lists, A-lists, and trees, even though they're all represented by conses.
Right.
So the implementation wouldn't know whether to call copy list or copy sequence or copy tree. Like it has no idea. Like
right. So when most people are talking about a generic copy, right? They're talking about a generic copy that behind the scenes it completely ignores the type information, like what type is being copied, and it effectively does a mem copy. Like that's what they're thinking of when they're talking about a copy, which I'm like, yeah, that's not, you can't, a mem copy is not going to, that's never always the case, right? Even in other languages that are doing copying, there's no way to write a proper generic copy method unless you're using that low level of a mem copy to do it. And even then, you might end up still doing a shallow copy because mem copy doesn't deal with pointers correctly. So I understand what Ken Pittman is saying. I just wish, I'm just wondering what would be the best way to handle it in terms of the structure.
No
yeah.
Best way. It's like on a case-by-case basis. There's no other way around it.
Right, but if we write in terms of other interfaces, is it possible to allow a template method to be constructed so that people can do copies? Is kind of a question of mine. So that way they know it looks like you are doing a generic copy, but behind the scenes it's whatever they specialized on. We're just using method specialization to actually go in and handle the pieces that are different based on the use cases. I don't know. I'm just throwing out ideas here at this point. I'm going to leave it at copy sequence for now, just because of the fact that it's probably the right thing to do given what we have, and then just write a note saying that we're not doing a deep copy right now. We're just doing a shallow copy. Again, I'm going to go and see what fset and Sycamore does in terms of constructing brand new sequences, and how they handle this particular case as well, to see if they fall apart.
I think Sycamore is a persistent data structure library, so that implies that it's always constructing new versions.
Right.
So there's I don't know. Yeah.
But how are they constructing it is the question. Are they, if it was just if it's just calling the type constructor, that's fine. But if they're calling some sort of copy function, then they're going to hit the same wall that this particular library is doing. Right?
Sycamore uses some of the techniques of closure, and that it uses a hash array map tree.
Okay.
Basically, it's hard to explain, but it's all a persistent data structure. You have multiple versions of each data structure, and you're immutably modifying it, but you still have the old data structure.
Got it. Interesting. Okay, that makes sense. Let's because I'm now literally wondering. I'm sure other folks have thought about writing this, and I actually found a Stack Exchange code that implemented it the way I would have implemented, which is they created a def generic. They've essentially wrote specializations on all the basic common Lisp types, and then for things that are dealing with structures and classes, they're using the mop. So what do? This is probably the best one of a given situation, since you have no other way of knowing of how to do structures of structures and doing recursive copies. So, so yeah. Hilarious.
Yep. And then you get into like infinite or circular sequences. How do you make a copy of that?
Right. Yeah. Well, it's interesting because, so just to give you guys kind of an idea on what one solution to work around this is basically, I'll do this ahead of time. We need to write essentially a couple of functions. One is essentially a def generic. We're going to call this deep copy, right, on some sort of object. Okay, and I'll write some documentation on this guy later on. So now we have our function. Let's go ahead and write some specific stuff related to sequences. And that is, let's go ahead and specialize this guy on, and I kid you not, this is I found some code that does it this way.
I think you have to like write a reference counting algorithm to copy arbitrary structures or classes, because you know a class can hold a reference to some instance of another class, which could hold
right. When it comes to objects,
cyclic graph there, so you got to know which ones you visited already.
Right. For objects specifically, I think you're going to have to end up writing what Sycamore does.
Topic.
What?
Point being, it's a complicated topic, and there's a million corner cases you have to deal with.
You know what? I'm gonna go ahead and write a couple things and show you guys next week, because what I'll do is I'll just implement this using Sycamore and stick it in there and saying, look, in terms of my implementation of the sequence interface, to get deep copies corrected, I just decided to use Sycamore to actually handle the handling, and I'll make sure I'll write a version of it for Sycamore sequences, so that way I don't have to deal with any of the copy semantics.
Also, I don't know what I just said about a reference counter, because a reference counter can't handle cycles.
Right.
It's a generational garbage collector for that.
I think copying itself is a topic in and of its own. You know, it's a lot. There's a lot of interesting things to talk about in terms of copying. Okay, other questions from the audience. Let's see who's left on our things. Okay, and for folks who are watching this stream, there's one thing that I want to make note of. Please provide some feedback on top of, you know, I love the questions and the comments about the font size and stuff, but if you guys want other topics to be discussed, please post your comments on YouTube. I tend to actually go back to all of my videos, and as for AFP's playlist curation, and I do go through those comments and respond to them accordingly. So if you just write a comment in the YouTube channel, whether it being a request comment or about the subject matter or what have you, we will get back to you. Probably even bring it up as part of a topic during our discussion during the streams itself. So until next time.
Also, for those who don't know, the Game Jam started yesterday. So if you want to partake in that.
I did not know that the Game Jam started yesterday. Oh man, okay, so that's great. Okay, so folks,
got plenty of time. It's 10 days long, so if you want to have some fun over the weekend and next weekend.
So folks watching, join the Lisp Game Jam. Let's write some games. It'll be fun. It'll be fun times. I think it'll be There's no theme this year, is there? This is not the themed base.
No.
Okay.
No, just have fun and see what you can write and just have fun. That's the idea.
Okay. Cool. Well, I'm encouraging you all to go and check out the Lisp Game Jam and do some Lisp hacking. Get used to writing some Lisp games. In addition, speaking of announcements, tomorrow Atlanta Functional Programming is having another meetup, another study group for Haskell. Our very own Judd Taylor is going to be presenting an introduction to Lambda calculus. It'll be a hoot. We did a beta run last week. I appreciate those of you who joined us last week to provide some initial feedback. We're going to be rehashing that talk a little bit, but with some updates. And hopefully some fun, albeit probably in funny discussion from the peanut gallery when we start going through Lambda calculus a little bit more in detail, especially within the context of Haskell. So those of you who are getting into who want to learn about Haskell, please join us tomorrow, same time, 1:30 to 3 Eastern Daylight Time, EDT. All right, please check your time zone to adjust, since we present all of our stuff in Eastern Time, both on the meetup as well as when we're presenting. So with that, I appreciate you guys joining me. I'll see you